Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we will be starting with metals and alloys. This is a subtopic of the new topic that we're starting today, which is metallurgy. Metallurgy is a very important component of your syllabus. So let's proceed. Let's go over the learning objectives. So you should be able to describe the general properties of pure metals as well as their alloys, the types of alloys and their uses specifically in dentistry. You should be able to explain the different procedures like cold working and annealing and their subsequent effect on the metal alloy. You should also be able to understand the cooling curves and phase diagrams of metal alloys when they are in molten state. Now, what is metallurgy? Basically, this is the study of metals and alloy and the science of extracting metals from their ores and applying them to useful purposes. In this case, obviously, dentistry. Now, I would like to ask you about your knowledge of metals, especially with respect to dentistry. Can you name any metals that are used in dentistry? Can you give examples where they are used? And can you enumerate the general properties of metals? And then finally, can you actually enlist any drawbacks or disadvantages of these metals? So now let's look at the application of certain metals. They are used in various instruments in surgical and dental procedures. They are used in the form of orthodontic wires. They may be used as components of metallic dentures, and they may be used as filling or restorative materials. So they have a lot of application and a wide range of uses in dentistry, and we will be covering all of them basically in the next lecture. An ore is a mineral containing one or more metals in a free or combined state, and basically when we extract our metals, so they are present in the form of an ore. They never exist like basically they never exist individually or in free form. So why use alloys? Why don't we use pure metals? So, as you know that pure metals are very soft and they have the tendency to corrode. So what is corrosion? Basically, this is the reaction of the metal with the environment, uh, which is commonly also known as rusting. So if we use pure metals in the oral cavity, as you know, it is a very dynamic and complex environment with changing pH and changing temperature, and saliva has its own physiology. So that can lead to corrosion and degradation. So that is why we cannot use pure metals. We have to use a mixture of two or more metallic elements, which are known as alloys, so that we can optimize their properties. Such mixtures are generally prepared by fusion of elements above their melting point. So, an alloy can be defined as a solid material formed by combining a metal with one or more other metals or non-metals, and so that we get optimal properties. There are many other definitions of alloys, but I think the best one is a crystalline substance with metallic properties that is composed of two or more chemical elements, at least of one which is a metal. But because we are talking about metallurgy, the alloys we will be dealing with will be basically a mixture of metallic elements. So they can be binary, they can be ternary or quaternary depending upon the number of metals present. And another term that we'll be talking about is basically a phase, which is a state of matter that is different in some way from the matter. Moving on, other terminologies, the microstructure. This is basically the structural appearance of a metal. If you look at it under the microscope, we refer it to as the microstructure. Crystal is a solid with periodic arrangement of atoms, usually with atomic planes forming facets. Now, what are facets? Facets are flattened and highly polished surface. And if you look underneath the microscope, this is how a metal will appear. It will have a flattened and highly polished surface. The crystal will have a very highly polished surface. And these surfaces are called facets. So, if we look at the crystal growth that occurs when molten metal, when basically metal is being melted and it solidifies, so the crystals, they tend to grow as dendrites from the central nucleus. Dendrites are basically three-dimensional and branched structures, and crystals continue to grow until all the metal has solidified and the dendritic crystals are in contact. So where the two dendritic crystals, two or more crystals come in contact, this area is known as grain boundary, and each individual crystal is known as a grain. Grains have the same dimension in each direction measured from the center of the nuclei. So, because there is an equal growth that is taking place when basically dendrites are growing, and the point at which they are coming in contact is known as the grain boundary. Equiaxial is basically the term used when because we've said that the dimensions of all the grain boundaries is the same and the axes have the same length. So if you can appreciate from the diagram on the right, this is an equiaxial or equiax grain structure. So a cast alloy microstructure in which all the grains have similar dimensions. And this is very important in dentistry, that we require equiaxial or equiaxed microstructure for the best properties. Then a crystal lattice is the arrangement of atoms in a three-dimensional space. However, in nature, the grains are not perfectly spherical, cuboidal, or any other geometric shape. However, they are said to have an equiax grain structure, and if there is any change in this equiax grain structure, it leads to change in the mechanical properties. So, a crystal was basically atoms with the arrangement of atoms in a regular in a regular plane with facets. A crystallite is basically a crystal with irregularly shaped surfaces instead of facets. Crystallization is the process of crystal and crystallite formation. Latent heat of fusion and latent heat of solidification. I'm sure you all have knowledge of these two terms. This is the amount of heat required to change 1 gram of substance from solid to liquid, called the latent heat of fusion, also known as basically melting. And the latent heat of solidification is the number of calories of heat liberated from 1 gram of a substance when it transforms from liquid to solid state. So this can also be called as, which is basically called known as freezing or solidification. Now, ductility, this is a very important property that is particular to metals, and you have studied this previously as well in chapter number 1, the properties of materials. This is the ability of a material to withstand permanent deformation under tensile stresses without fracture. As you all know, tensile stresses are the pulling and the stretching forces. So basically, the ability of a material to deform plastically or permanently under these tensile stresses before fracture also can be called the ability of a metal to be drawn into wires. If you appreciate the stress strain graph on the right, so this is basically a graphical representation of two metals, one which is depicted by the blue graph and the other by the red graph. If you look at the blue graph, you can see that after a certain amount of stress, there is a very small degree of strain or plastic deformation before it fractures. So this means this kind of material can be said to be brittle. And on the other hand, the red graph depicts a material that after a small amount of stress undergoes a considerable amount of plastic strain and finally fractures. So this kind of material can be said to be ductile. Now moving on to other terminologies, crystallization, which is the transition from dissolved molten liquid or gaseous state to the solid state with the assumption of a crystalline form. Recrystallization, when a normal crystalline structure is re-established, and recrystallization is that temperature at which the distorted grains are replaced to a new stress-free uh, organization with regular space lattices being about half the melting temperature of the metal. Now, the general properties of metals. So, firstly, they are hard and solid at the ambient temperature, except which metals? Can anyone tell me which metals are not solid at room temperature? And they can be polished to a luster. They have a crystalline structure. They are usually opaque and good conductor of both heat and electricity. They have the ability to donate electrons due to free electrons, and hence they are malleable and ductile and can be easily shaped. And they have excellent mechanical properties. Now, shaping of metals and alloys. Why is that important? Because in dentistry, we cannot use the metals in their original form. We have to give them certain shape and dimension and structure for to be used in the oral cavity, be it as a restoration, be it as a prosthesis. So there are three methods of shaping metals and alloys: casting, cold working, and amalgamation. Casting we have covered in the previous topics, and I'm hopeful you're all very familiar with the. However, let's just go over it once again. Heating the material until it becomes molten, when it can be forced into an investment mold which has been prepared from the wax pattern, which, as you all know, by the lost wax process has been burned. The procedure involved the wax pattern, attachment of the sprue to the pattern, placement into the casting ring, investment poured, wax and sprue removed by dewaxing, and finally casting by the flow of the molten metal. So that was casting. Now let's move on to cold working. Cold working is also known as strain hardening or work hardening. It is the strengthening of a metal by plastic deformation. So this involves the strengthening of a metal by plastic deformation at room temperature without application of heat. That is why it is known as cold working. So there is no application of heat and it is done at room temperature. And the strengthening occurs because of the dislocation movements and dislocation generation within the crystalline structure. Because of the free electrons that are able to move, we are able to give the metal or alloy the desired shape at room temperature. So simply it can be said as the mechanical shaping of the metals at a relatively the mechanical shaping of the metals at relatively low temperature, and we are able to achieve cold working by taking advantage of the high value of the ductility and malleability of the metal. So this is very important. The definition of cold working is often asked, so you should be able to write down the proper definition. Now, what are the effects of this procedure? The effects of cold working are: firstly, the properties of the material are completely changed due to this procedure. There is an increase in the mechanical strength, which is the compressive strength, the increase in hardness, and it shows a higher value of yield stress. So that means more stress needs to be applied in order to plastically deform it or fracture it. However, there is a decreased ductility or malleability because the potential for further cold working is reduced, and that is why it is also known as work hardening or strain hardening. You will find these terms as well in other books: work hardening, strain hardening, or cold working. They are more or less the same thing. Now, if you are asked about the examples of cold working, well, you have done it yourself and you'll be doing it as well. The bending of wires and clamps during the construction and alteration of appliances. If you can see from the picture, this is basically a picture of a partial denture, and these metallic round shape things are the clasps, and you'll be making these clasps in prosthetics as well as in our dental materials practical next week. You will be asked to make the C-shaped and S-shaped clasps. So that will be an exercise of the wire bending so that you can get an idea of what cold working is. And again, why it is called cold working? Because this is being done at room temperature. In the same way, in the second picture, if you can appreciate, these are the orthodontic brackets through which the wire is passed through and attached. So this also practice is known as cold working, because at room temperature these wires are inserted into the brackets and passed all around. So these are two examples of cold working. The third example is a process known as swagging. Swagging is basically a process by which stainless steel denture bases are formed, As you can, if you can recall that we said that denture bases are made up of basically two main materials. They can be metallic and non-metallic. So the metallic denture bases, if they are made of stainless steel, the process by which we make the denture bases, we adapt the stainless steel sheets onto our cast, and that process is known as swagging. So these are the three examples of cold work. Now, cold working has seen to cause the formation of internal stresses, and if they are gradually relieved, they can cause distortion, leading to loss of fit and malocclusion in orthodontic appliances. So, they can be eliminated by using low temperature heat treatment called stress relief annealing, and that we'll be talking about annealing. So, after cold working, another heat treatment or process is done, which is called annealing. So what we do is we heat the material to above its glass transition temperature. As you know, the glass transition temperature is the temperature at which there is a slight increase in the molecular mobility of the molecules. It is well before the melting point, and it is just a basically temperature change where there is slight softening. So, if, annealing is done by heating the material to above its glass transition temperature, maintaining a suitable temperature, and then finally cooling. This is known as annealing. Why is it done? To induce some form of ductility and soften the material, to relieve the internal stresses, which is the most important point, and to refine the structure by making it homogeneous and improve its cold working properties. So these are the three reasons why we need to carry out annealing, and it is always done right after we do the cold working. So you can kind of say it is the opposite of cold working, because you are achieving softening and you want to relieve the internal stresses that are created due to cold working. And at the same time, it improves the cold working properties by giving a refined and a regular structure. Now, just a little bit about the structure and properties of metals. Metals have crystalline structure in solid state. So when the molten metal and alloys are cooled, solidification process starts at different sites called nuclei. So these are basically the nuclei, which are the single centers or sites from which the dendrites will arise and crystal growth will occur. This is how it actually takes place. This is the molten liquid metal. These are the small nuclei that acts as center for crystal growth. Dendrites continue to grow, and where these dendrites merge or they come in contact, these are called the basically grain boundaries of the crystal. And as the dendrites grow, the spaces between them fill in. So this is basically the process by which solidification of molten metal is taking place and grain growth is taking. Now, an important thing is that basically there are defects that occur naturally within the crystalline structure, and they are called dislocations. If you can see from the arrows, these are basically those points from which the molecules can easily move, and these are the basically reason why the metal is known to be ductile. So specifically, the free electrons, they tend to move along these planes, and they are called dislocations. And the plane along with dislocation moves is called the slip plane. And the stress that, or the force that is required to initiate this movement is the yield stress. So a specific amount of stress is required to initiate the dislocation or the movement, and this leads to the ductility. If we look at the arrangement of metals, well, the atoms within the grains are arranged in a three-dimensional lattice. And there are many different kinds of arrangements, but we will be just talking about the arrangement of metals in dentistry. So there are basically three types. It can be arranged in a cubic form, in a face-centered cubic form, or a body-centered cubic form. And the corresponding pictures on the right, A, B, C, actually correspond to these types. You have the cubic form, the face-centered, and the body-centered. Now, the arrangement adopted by the crystal depends on specific factors like the atomic radius, the charge distribution, and there are other factors that actually give rise to its crystalline structure. Now, if we talk about the movement of dislocation, which owes to the ductility of metal, this is basically dependent on the grain boundaries. The grain boundaries, which you know, are the point of contacts between the crystal or the grains, basically, they form a natural barrier to the movement of dislocation, and they try to prevent dislocation in the normal form. The concentration of grain boundary increases as the grain size decreases. So the finer the grain is, the smaller the grain size is, the concentration of grain boundary increases, which means it is more resistant to the movement or dislocation. So metals with finer grain structures are harder, which means they are more difficult to basically give any kind of movement or dislocation, and have higher values of yield stress than those with coarser grains. So we prefer metals with finer grain, but the only drawback would be that they would be less ductile. Metal properties can be controlled by controlling the grain size. So if you want a more ductile metal, what you can use is that you can try and make the grain structure coarser and irregular. So what that will do is that will make the concentration of grain boundaries, will decrease it, and that way the movement or dislocation will be easier to take place. Now, how can you achieve fine grain structure? Fine grain structure can be achieved by rapid cooling of the molten metal. This process is called quenching. Quenching is simply the rapid cooling of molten metal, and this increases the nuclear crystallization, resulting in a large number of relatively small grains. And as you know, the smaller and the finer the grain, the more harder and resistant the metal. Slow cooling causes relatively few nuclei to be formed, which results in a larger grain structure. Refined grain structure can also be achieved by seeding the molten material with an additive metal. So these are basically two ways by which you can achieve a refined grain structure. One is by quenching, and the second is by seeding or applying additive metal into the molten material. So these changes occur when the stress is greater than the yield stress. As I mentioned, that yield stress is basically required to cause the dislocations, and when the applied stress is greater than that at a low temperature, these dislocations occur. And in cold working, there is not only a change in the mechanical properties and microstructure, the grains become fibrous rather than equiax. So as I mentioned, that our metal and alloys are equiax in the natural state, but when we carry out cold working, if you can appreciate from the diagram A, it shows that the cold work metal becomes more fibrous in its structure after we carry out cold working. So now let's move on. Now we'll be talking about the molten form of alloys. So it is seen when the molten metal is cooled to below the melting point, one of the four things can occur in it. Either it can become soluble in each other and form random solid solution, ordered solid solution, or an interstitial solid solution. These are the four possibilities that can occur. And it is seen that in molten state, metals usually show mutual solubility. So if we talk about them individually, so we said the metals may remain soluble in each other and form a solid solution. Now this solid solution may be of three types. It may be a random solid solution. By random, it is self-explanatory. It means that the metal atoms occupy random sites in in a common crystal lattice. If it's an ordered solid solution, the metal atoms occupy only specific sites within the crystal lattice. And if the metal atoms lie within the interstices of the lattice, the interstices, as you know, are basically the boundaries on the interstices of the lattice. So these are called, such a solution is called as an interstitial solid solution. Similarly, an intermetallic compound may be formed, and basically if there are two metals who show particular affinity or attraction for one another, They may form an intermetallic compound. An example is silver tin, which is formed in amalgam. We will be studying dental amalgam after we are done with metallurgy. So, in during the setting of dental amalgam, this silver tin phase is formed, and this is an intermetallic compound. So, it has a precise chemical formulation and specific valence requirements. And the important thing is that in intermetallic compounds, there are very few imperfections or dislocations. Hence, the potential for movement along the slip plane is reduced. So that means dislocations are very less and they cannot move that easily. That is why intermetallic compounds are hard and brittle and they have low ductility. Now, finally, we will be talking about some graphs and curves related to the solidification of molten metal and alloys. It is very important and it can be studied graphically. And what we do is we plot the temperature versus the time or the composition. So let's look at the cooling curves. So metals and alloys may be characterized by using cooling curves. So when the metal is heated until it is molten, it is then allowed to cool and solidify. Now, the first graph on the right, this is of a pure metal. Okay, so there is no alloy. It's not an alloy. It's a pure single metal. And if you can see that the cooling curve shows that first there is a temperature drop, and then from Tm onwards there is a distinct plateau region, and this is the melting point, and this indicates that and another an important and interesting fact is that the temperature remains constant during this time. As you all know, I'm sure that when melting is taking place, the temperature remains constant over a period of time during crystallization, and then again there is a sudden drop in the temperature when it starts to cool and solidify, and this all takes place over a certain period of time. So now this was the cooling curve of a pure metal. In case of alloys, there is usually no such plateau region. As you can appreciate from the second graph, this is basically of an alloy, and there are two temperatures T1 and T2. There is no plateau region. Crystallization begins at the temperature T1 and is complete at temperature T2. So crystallization, rather than taking place at a certain melting point, takes place over a range of temperatures. Why a range? Because there are more than one metals involved. So let's look at the graph in detail. A pure metal is melted and allowed to cool to room temperature. The, the graph of the temperature against time is plotted, and as you can see, the temperature decreases gradually from point A to B. So this basically what is happening is melting is taking place, and then a sudden increase in temperature or a spike in the temperature occurs from B prime to B, and then the temperature remains constant from point B to C, and subsequently the temperature of the metal decreases to the room temperature, which is D. An ore is a mineral containing one or more metals in a free or combined state, and basically, when we extract our metals, so they are present in the form of an ore. They never exist like basically they never exist individually or in free form. So those were the cooling curves for pure metals. When we talk about alloys, which is a mixture of two or more metals, we call them phase diagrams. So the series of cooling curves for alloys of different composition within a given alloy system are called as phase diagram. As you can see from this particular type of graph on the right, So this shows different phases of alloys during cooling. Now, if we consider a hypothetical solid solution of a metal A and B, again as you can see on the y-axis we have the temperature and on the x-axis we have the percentage composition. So basically from this graph we can determine at which temperature the specific composition at the different temperatures. Melting points of pure metals are indicated by TMA and TMB. As you can see, the melting point of A is definitely higher than the melting point of B, and upper and lower temperature limits are shown by T1 and T2. So what can we identify or uh, find out from this graph? Well, at the different temperatures T1 at different points, we can find out the composition. So if you look at the first point T1, we can see that at this temperature the composition of metal A is 80% and that of B is 20%. And moving ahead, if we go to the last point, which is again T1 near to the melting point of metal B, A is 20% in composition and B is 80%. So at different points in the temperature we can find out the composition. So for a binary solid solution, again A and B, melting point of A is obviously higher than that of B. First metal to solidify is A. First material to crystallize at just below temperature T1 will be rich in the higher melting point metal A. And last material to crystallize at a temperature just above T2 is rich in the lower melting point metal B, and which is 80% of B. So, so as you can see, these graphs are very useful for calculating the composition of the metal at that particular point of temperature. Another important thing is that from these phase diagrams, we can determine what state the alloy is in. At temperatures above the top line, as shown by this first red arrow, the alloy is totally in liquid state. And this temperature is known as the liquidus temperature. And at the temperature below the bottom line, also shown by the second red arrow, the alloy is totally solid. These temperatures are known as the solidus temperature. And this phase diagram is completed by joining all the points of T1 and T2 together with the melting point of A and the melting point of B, and this is called the phase diagram. Now, what about the region between the solidus and liquidus line? This is basically where there is a mixture of both the solid and liquid phase of the alloy. The solidus and liquidus temperature are very important and they are often asked. We are asked what they are and where on the graph are they present. So the phase diagrams can be used to predict the characteristics of an alloy. The composition of the solid and liquid phases at any temperature between T1 and T2 can be predicted. For example, a composition of X, alloy of composition X, of which has approximately 60% A and 40% B. If the alloy is cooled from above the liquidus, it will remain molten until the temperature is reached where the first solid begins to form. So all of this can be predicted with the aid of this phase diagram. Now phase diagrams, you won't be asked to plot them, or you were rarely asked actually anything about them, but what is important that you should know why they're used and what you can actually predict from them. And the second thing, the most important thing, is you must know what a liquidus temperature and solidus temperature is. It's just the basic general idea of these graphs. Now, a very important thing that can occur during the cooling of these alloys is a phenomena called coring. Coring is when an alloy cools in a non-equilibrium condition, and this causes the exterior of the material to solidify before the interior. So now what does this lead to? It causes the centers of the grain to retain more of the higher melting temperature, and this leads to detrimental properties, especially a decrease in corrosion resistance. As you all are aware that metals undergo corrosion, and we try to improve one of the properties that we try to improve is the corrosion resistance. We want a metal or an alloy that is more corrosion resistant corrosion resistant. Why? Because once it goes into the oral cavity, as you all know, the oral cavity is a very dynamic and complex environment which has saliva, which has its varying pH and varying temperatures. So that is why, because of the change in the environment, and it's a very hostile environment, uh, any kind of foreign metallic restoration or prosthesis can undergo corrosion. So that is something we want to, if not eliminate, we try to keep to the minimum. So coring has seen to lead to decrease in corrosion resistance, which means that it makes the alloy more prone to corrosion. So how can we eliminate coring? With slow cooling. The crystallization process by diffusion and random distribution of atoms, no coring. What happens if the solid solution is cooled rapidly? Rapid cooling denies the alloy of the energy and mobility required, and that results in basically coring. And reducing the cooling rate as a means of eliminating coring, self-defeating, produces alloys with large grains, and that leads to inferior mechanical properties. So our aim should always be to try to eliminate and prevent coring, and the best way is by allowing slow cooling to occur. Also, we can carry out homogenizing heat treatment, in which the alloy is heated to a temperature below the solidus temperature for a few minutes to allow diffusion of the atoms and establishment of a homogeneous and regular structure. And then again, like with all the treatments, quenching is carried out to prevent grain growth. Now moving on to the eutectic and peritectic alloys. These are basically two types of alloys, and they have their own unique phase diagrams. Again, you just have to know the definition of eutectic and peritectic alloys and just know that what the graph looks like. You will never be asked to plot it or label it. You just have to, like I said, know that what the graph looks like, what is present on the y and the x-axis, and the liquidus and solidus temperature. So in this graph, which is basically a typical graph of the eutectic alloy, the alloy with composition corresponding to point C, which is where basically A and B, it is basically a temperature which is similar to the metal A and metal B. This is called at this point, this is called a eutectic alloy. And this crystallizes at a given temperature and not over a range of temperatures. Like we saw in the previous alloys, that there is a range of temperature. So at this point C, basically, it is called a eutectic alloy. Some metals are completely insoluble in solid phase, and alloy of such metals consists of a mixture of grains of the pure metals. So hypothetically, again, we are taking two metals A and B. To the point, to the left of the point C, the pure metal A, it is always pure metal A, and to the right of the C is always the pure metal B. Solid is always pure metal, and point C is basically a mixture of both A and B, and it is also called the eutectic alloy. And the important feature is that it crystallizes at a given temperature and not over a range. Uh, and eutectic alloys are usually used for the process of soldering, which we will be discussing in the coming chapters. It is also a process by two metals are joined together, and eutectic alloys are preferred for this procedure. I have simplified the definitions of both eutectic and peritectic. They have been asked previously in the UQs, and this is all you have to know about them. Firstly, you have to be able to recognize the graph. The first graph is typical of a eutectic alloy, and the second of a peritectic alloy. And eutectic alloy can be simply defined as an alloy of two or more metals, which, when heated to its melting or solidus temperature, will completely change from solid to liquid at the same temperature. A classical example of eutectic alloy is silver copper in case of dental amalgam. As I mentioned, when dental amalgam is setting, there are different phases that are formed, and when silver copper is formed, it is basically a eutectic form or phase, and this is how the graph looks like. And in case of a peritectic alloy, the graph is a bit more complicated, as you can see. So when a liquid phase of fixed composition reacts with a solid phase of fixed composition at a fixed temperature, not again uh, under a range of temperature, it forms another solid phase. This reaction is known as a peritectic reaction, where there is a major difference in the melting points. As you can appreciate from the graph, there are two metals and there is a major difference in their melting points, vast difference. This kind of alloy is known as a peritectic alloy, and an example again in amalgam is the silver tin phase. So this is all you need to know about eutectic and peritectic alloys, and we have reached to the end of our today's topic. I hope it's all clear and you know what you are required to, how the extent of knowledge you are required to know regarding this topic. And still, if you have any questions, please feel free to ask me. So this brings us to the end of this topic. So in case of a peritectic alloy, because there is a major difference between the melting points, there is more potential of coring. As you can see, there is a wide separation of the solidus and liquid lines. So peritectic alloys are more prone to coring, and as mentioned in the previous slides, again that we can control by carrying out homogenization and gradual cooling. So that can eliminate the coring.